We'll continue from the last video, and today we'll do the second sum. Let's read the sum first. In the figure, two circles touch internally at P. From an external point Q on the common tangent at P, two tangents QA and QB are drawn to the two circles. Prove that QA equals QB. So the first step that I always do for these kinds of sums or riders is whatever sum has been given to me, the data that has been consolidated in the sum in written form or in theoretical form, I try to give a visual representation and essentially see what has been given to me on paper. So I try to make a visual representation. So since I've already drawn the diagram, let's tally with the data, the theoretical data that we have and the visual representation, that is the diagram that we have. So in the figure, two circles touch internally at P. So you see we have two circles which touch internally at P. Needless to say that these two need to have different radii, because if these two circles touch internally at some point P and they have the same radii, it's quite impossible that they have the equal radii, otherwise these two circles will coincide with each other. So that's a given, the fact that these two have different radii. And what I can do is, since these two have two separate centers, what I can do is I can name this center as X. So that's the center of the bigger circle, because that is further away. So if you have a bigger circle, it means your radii for that circle will be larger. And I can name the other center as Y. So that would be the circle which has the smaller radius. The circle with the smaller radius has the center Y, and the circle with larger radius, XP, essentially has radii XP. So that's the setting that we have for this kind of sum. Next, what we see is from an external point Q and external points. They haven't given any particular position, but what they have said is it needs to be on the common tangent at P. So we know that these two circles under consideration, they touch each other internally at point P. Now, why they have mentioned internally is if two circles touch each other, if two circles touch each other externally, if two circles touch each other externally, then we have a situation like this. But if we have two circles which touch each other internally, then these two circles, it's not a circle. Let's use this. Yeah. Then we'll have a case like this. So these are two circles which touch each other internally. They don't look like a circle, but yeah. This is the case where the two circles touch each other internally, and if the two circles are like this, then they are said to be touching each other externally. So that's a small definition that we need to remember for this sum. Next, what we see is two tangents QA and QB are drawn to the two circles. So from this point Q, which lies on the common tangent through this point P, we have drawn two other tangents to these two circles. So QB is the tangent that is drawn from point Q to the circle with the smaller radii, and QA is the tangent that is drawn from the point Q to the circle with the larger radii. And what we need to prove is QA equals QB. So this sum essentially requires a very important theorem of the transverse of tangents and circle. But if you know the theorem, then that makes life much easier. So I'll just briefly talk about the theorem, and I'll straight move on to the proof of this sum. So what essentially the theory says is, if say you have a circle, let's take the bigger circle. So say you have a circle and the center of the circle is at point X, and from some external point Q, whichever point it be, from any external point Q, you draw two common tangent. You draw two tangent. Just forget. Let me. How do I remove that? Select. Now, better. So what we let's take for the time being this bigger circle, which has a center at x, and from an external point Q, we draw two tangents, which each of which meet or touch the circle at point P and A respectively. So you have tangent AQ and tangent PQ. The corresponding radii are XP and XA. Forget about B for the time being. So if that is the case, then what we can do is we make a small construction. Let's join these 2 points XP and XY, and let's join AQ and let's join PQ. So what we see in that case is, since AQ is tangent to the circle, that essentially means XA is perpendicular to AQ. So this is a right angle. Similarly, this must also be a right angle since XP is the radii of the circle whose tangent is PQ. So these two angles, if I consider XPQ and XAQ, then these two angles are equal. XP and XA are radii of the same circle, which essentially means XP should be equal to XA because a circle cannot have more than one radii. So they are also equal. And this line segment XQ is common for both triangles. So essentially XQ is an equal length for both these triangles. So you see, we can consider these two triangles to be congruent to each other. XAQ is congruent to XPQ, and the rule for congruency in this case could be right angle hypotenuse side, so RHS, right angle hypotenuse, that's the side which is opposite to the right angle, and one side. So we can consider RHS congruency for these two triangles XAQ and XPQ. And if these two are equal, then what we can say is essentially AQ, let me mark it separately, AQ and PQ are equal because they are two corresponding sides of two congruent triangles. And we can say that AXQ is equal to PXQ. So yeah, and essentially even these two angles are equal. So we don't need so many corollaries or so many results from the theorem, but that is what the theorem essentially states. AQ for any two tangents which are drawn to a circle from a particular external point, the length of those two tangents essentially is the same. They subtend equal angle at the center, and these angles are also equal. So that is the basic theorem. But in this case, we'll essentially, for this sum, essentially, we'll just need the fact that the two lengths of the tangents are equal. So let's go back to the sum. So we already proved that AQ should be equal to PQ. So if Q is an external point on any external point essentially, then for the bigger circle with the center at X, that is what I used to prove the theorem, we can say that AQ is equal to PQ because they are both tangents to the bigger circle which is drawn from an external point Q. So that is the second second equation that I've mentioned here. So AQ and PQ are two tangents, which essentially means AQ equals to PQ. That same logic can be applied to the smaller circle, which has its center at Y, and Q being an external point, I can draw tangent BQ and tangent PQ from this external point Q to this circle, smaller circle, which has its center at Y. So BQ and PQ are also two tangents, which using the theorem that I proved earlier, BQ is also equal to PQ. Now, look at equation 1. It says BQ is equal to PQ. Again, look at equation 2. It says AQ equal to PQ. So it's like saying BQ equal to PQ equal to AQ. So automatically from these two equations, I can conclude that AQ equals PQ. So you see, this sum essentially does not require a lot of theory and calculations and mathematics. If you just simply know this theorem that this sum follows from, you can do it in what like literally 5 steps. So that's a very interesting sum in the sense that it does not require a lot of calculations like the previous sum that we saw. It has various steps and it has various layers to it, but this sum is not that difficult. So this is also an interesting sum from the chapter on circles.